Hello. In this video for Chapter 18, we're going to discuss something known as the leveling effect. So as we've discussed up to this point, we are measuring acids in the presence of water, with water acting as the base, to form a conjugate base and H3O plus, the conjugate acid of water. Okay, we could also, and so the K expression for that, Ka, the acid ionization constant, it's going to equal the concentration of A minus times the concentration of H3O plus all over the concentration of HA. We could do the same for a base. Okay, in this case, I'm just going to use A minus, the conjugate base, since we'll treat this as a conjugate acid-base pair. Okay, and now water is going to act as the acid in this example, reforming the conjugate acid form of A minus HA, and then, of course, OH minus. And thus, the Kb for this expression, so the Kb expression for this reaction would be the concentration of HA times the concentration of OH minus all over the original the concentration of the original species A minus. All right. So generally, and I'm gonna move these up here. So here we've got acids. Over here we've got bases. Okay. So the table that we see here on the left side we have Ka values, and on the right side we have Kb values. Okay, and these are conjugate pairs. Now, for the sake of later discussion, I'm going to identify where water is on this table. And so water and its conjugate are here. And you see here, right here. That'll be important here in a moment. So we could see a wide variety of values here. We've seen this species multiple times, but let me find it here. 1.8 times. Yeah. So for example, there's acetic acid. Can find, for example, the ammonium ion and its base form ammonia. As an example also from class, where's cyanide? Where's hydrogen cyanide? Oh, it's right down there. Well, let's pick carbonic acid instead. Okay, so we have a variety of different values here, and you'll note that because these are conjugate acid-base pairs, do not forget that Ka times Kw for any conjugate acid-base pair is going to equal 1.0 times 10 to the negative 14th. Okay, so for example, here we go. For example, we could look at 1.8 times 10 to the negative 5th times 5.6 times 10 to the negative 10th. That's going to give us 1 times 10 to the 14th. So what is the leveling effect of water? Well, let's look at hydronium as an acid, and then let's look at water as an acid in itself. So okay, so if we look at these, H3O plus with water, the conjugate base of H3O plus is H2O, and the conjugate acid of H2O is H3O plus. So if we calculate, if we set up the Ka expression for this, we get the concentration of H3O plus at equilibrium divided by the concentration of H3O plus at equilibrium, which is simply 1. We can see that here. Okay. Now, on the other hand, if we have water acting as an acid, in water acting as a base, then the conjugate base form of H2O is OH minus, and the conjugate acid form of H2O is H3O plus. And so if we write the Ka expression for this, we get the equilibrium concentration of OH minus times the equilibrium concentration of H3O plus. Well, we know that is simply Kw, which we can see right here. Okay? We're going to see the same thing on the other side if we look at the base forms of things. Same thing. Okay? So everything we're doing on the acid side, it's on the base side just flipped. And so note here, going from up, it's increasing acid strength. And so here's the issue we run into. For any acid that has a Ka that is greater than 1, okay, meaning it's very product favored, well, we're only going to be able to get a value of 1 as the Ka if we try to calculate it. I mean, it can go over, but we're trying to measure in water, and the strongest measurable, well, actually, we'll just say strongest acid. The strongest acid in water is hydronium. Okay, anything stronger just becomes hydronium. So if we put HCl in, it just gets 100% converted to hydronium. And Cl minus. If we put in nitric acid, same difference. Okay, so anything that's a stronger acid than H3O plus just becomes H3O plus in water. So we can't measure these values. You can see they just say large. The same holds true on the bottom end, right? Any acids weaker than water, well, then water will act as the acid, right? And so anything that is a worse acid than water that you put in water, the strongest acid is what is going to generally react. And so you're not going to be able to see it, right? Water will act as the acid in that case, if possible. And so these are also effectively immeasurable. Now, there does seem to be an example or an exception here for the hydrogen sulfide ion, but let's skip that for now. Okay? We don't really care about that. So there seems to be a cap on what values of K we can measure in water. And it's entirely because water is our reference for calculating the strengths of acids and bases. Okay? So this is called the leveling effect of water. So again, the strongest acid in H2O is the strongest acid in H2O is H3O plus. I'll move it up here. And the strongest base in H2O is OH minus. Okay. The weakest base in water is water, and the weakest acid in water is water, with a Ka value of Kw in the case of H2O as an acid, and H2O as a base, and base. Oh, give me one moment here. And the weakest base in water is, of course, again, H2O. So again, leveling effect of water. So how then would we measure strong acids? Because remember, right, the reason we call these strong acids is because when water is the environment, they will 100% ionize, right? They're too good of an acid. Okay, they're too good of an acid in water, and so they pretty much 100% donate their protons to water. So how do we measure Ka values for these if we can't use water? So what do we need? We need a weaker base than, we need a weaker base in solution. We just need a weaker base in water. And so what would be a good weak base? So let's write HCl as the acid here. So what would be a good weak base? Well, remember, anything that's got lone pairs on it can act as a base. So if we force acetic acid to act as a base, which will happen because if HCl is the stronger acid of the two, then this will be forced to act as a base. And so then instead of aqueous, I'll put AC for acetic. And so if we run this in pure acetic acid, so just like we used water as the medium for measuring, we're going to use acetic acid as the medium for this. Well, then we would get Cl minus AC. We're going to have stand for acetic acid. We could have put AA as well. And then, of course, the conjugate acid of this would be H2C2H3O2 plus, as it would be forced. You're protonating something that normally wants to lose a proton. Okay? And if we do this, we can measure a K value for this at this point. Okay? And in fact, we would find that the K value for HI will be the highest, followed by HBr, followed by HCl, which matches up with bond association energies and what we know about the strength of bonds for these diatomic heteronuclear species. Okay, so if we want to measure things stronger than H3O plus or OH minus, we got to use something different than water. Otherwise, you can measure it in water. Okay. All right. That is it for the leveling effect of water.